They can hear me and stuff. I don't think they can see. Is there a way for them to see the camera? Can somehow do this or whatever.
From the smaller screen and the
You mean they see the room from this camera? Can they hear me? That's the question. Because I think maybe.
Do the online audience hear the room?
We do hear you perfectly fine.
Yeah.
And if I stand here, can you still hear me?
Can you say something?
Yes.
Okay, too far. Can't hear anything.
Okay.
Yes.
Great. So thank you for the introduction. So I'm Hemi, and today I'm going to talk to you about CMoSS, the Composable Modular Security Specification Framework. This is a joint work with my great collaborators. So I will just show you their mugshots first. Okay. Sarah Vorotniak, am I somewhere, right? Which is a brilliant PhD student here. Professor Evaseta from Trinity College and the National Research Institute in Poland. Professor Herzberg, also from Yukon, myself from the College of Management Academic Studies of Israel. And so the basic talk today, the outline of this talk, I'm going to make it a three-part, basically. The first part is what is the problem that we're trying to solve in this work, and not only what, why are we trying to do that? The Cliff Note version, basically, is going to be the analysis of security. The security analysis of complex protocol is very, very important, but it's not that trivial. And the idea is to develop a framework that will allow us to do it in a much more possible way, but not only possible, that we actually be able to capture some non-traditional, not traditional, realistic models, and not like it's being done currently, which I will elaborate later. Then I will kind of continue the motivation of this question into the state of the art. I will basically mainly talk about the game-based approach, but I will also mention UC. And then I will concentrate about CMoSS, which is an extension of another work called MoSS. And I will elaborate on that. So, what is the problem that we're actually trying to solve? Rigorous analysis of security of the security of protocols, especially cryptographic protocols and applied protocols, is very, very important. And this is so important because we are actually grown accustomed to expect that. Whenever you are working on designing a new protocol, it is expected of you to actually present a provable, formal rigor analysis of the security of the protocol. Right? When we are as readers, we want to say, oh, it's a nice design, but we want to also be able to actually grasp whether it is secure or not, whether it satisfies some properties, some requirements or not. Now, in reality, that sounds nice, but in practice, there are a lot of challenges of actually doing so for complex protocols. And when I say complex protocol, it is mainly applied protocols, but definitely not only applied protocols. And also to analyze such protocols under realistic assumptions. And this is very, very hard. We actually learn it the hard way ourselves, because we didn't wake up one day and say, you know what, let's design such a framework. We actually wanted to develop a framework or a protocol which was about to use PKI as an underlying protocol. But when we try to, as we expect from ourselves, right, to produce rigor analysis of the security of our protocol, of the protocol that we want to design, we tried to use the existing methods, and it was very, very hard. We were not happy with the result, and at some points we even got really stuck on how to do it correctly in a way that will be happy. So why is that? Complex designs it's very hard to capture what are the definition and how you actually going to prove whether these definition, these requirements are actually achieved or not. You have to capture a lot of very, very subtle assumptions and sometimes not so subtle, and all take into consideration clock synchronizations and network drifts and all kinds of assumptions, which makes the analysis significantly more complex. Now, I want to give you a small example that, for example, maybe some of you, I mentioned that we were working on a protocol that was using a PKI as an underlying protocol. So maybe some of you are familiar with a system called CT. It's a form of a web PKI. It operates in the web ecosystem. And CT, certificate transparency, I want to read you the first sentence for RFC 6962, which defines certificate transparency version 1. So certificate transparency aims to mitigate the problem of misissued certificates by providing publicly auditable, append-only, untrusted logs of all issued certificates. Now, you don't need to be familiar with CT. My idea here is to show you there is a system that clearly states that they want to mitigate the problem of misissued certificate. That's their goal. And they're going to assume untrusted logs. You can't be more clear than that, right? However, when we try to actually do analysis of a PKI and we wanted to say, hey, how other people have analyzed PKI-based protocol, right? So we tried and we explored and we actually were uneasy about this definition, this kind of statement, because we came into the conclusion that you cannot really achieve the stated goal when you assume untrusted logs. And we went to RFC 9162, which defines the improved version, right? CT version 2. And then you can see relatively in the beginning that they have these two sentences. The log auditing mechanism described in this document can be circumvented by a misbehaving log that shows different inconsistent views of itself to different plans. Therefore, it is necessary to treat each log as a trusted third party. So you can actually see that in the new and improved version, right, they actually revised this statement. And I guess that behind the scene, I can only assume, right, when they firstly said this, because this is what this was their intention, this was their goal. But in practice, they could not completely achieve that under the assumed model, so they had to revise it. Okay, and this is a phenomenon that we're kind of one of the phenomena that we want to avoid. We want to be able to say, if you would have a provable analysis that I could have verified, right? So every claim that you make, I can actually verify, right? You have to prove it, and if you won't be able to prove it, there will be a reason, so you won't make this claim. So we want to decrease the chances of actually making such mistakes or, right, imperfections from actually happening. And this is just one example, right? The subtleties that can go unnoticed, but there are many other characteristics that you can find in existing works and existing research. So for example, a lot of abstractions that the researchers do in order to have analysis of the protocol, a lot of informal arguments, because when you do informal arguments, you can get away with a lot of the challenges that you need to face. And you have my personal favorite as a phrase not to use, proof by intimidation, when you just provide 10, 20, 100 pages of proof, and you kind of say, good luck proving me wrong, right? So it's kind of, this is a proof, it may be correct, maybe not. Let's see if you can disprove my analysis, right? And this actually, all these characteristics result in a serious thing that we can actually, it's very hard to compare protocols. So you would really want, right, to be able to take one protocol and compare whether it's better or not with comparison to specific properties under specific assumption. But if different protocols that try to solve the same problem, right? If they are using different terminology, if they define the same requirement slightly different because they have different entities in the system, right? It's really, really hard to compare, and you cannot compare apples to apples like you would have wanted, right? Great. So this was the first part of the motivation of showing, discussing a bigger problem. What I'm going to do now is move to the next. I'm going to discuss game-based approach to actually prove and analyze the security of schemes and protocols. And I'm going to take the very simple signature scheme. And the reason that I'm going to do that, I'm going to show you how it's done with currently game-based approach in order to contrast it to MoSS and CMoSS, the work that we actually want to discuss later. So a traditional signature scheme, right, is a set of 3 algorithms, key gen, sign, and ver, where the key generation gives you a signing key and a verification key. The sign algorithm takes the signing key and a message M and outputs a signature sigma, and the verification algorithm takes a verification key, message M, and a signature sigma, and outputs true or false, whether the signature is a valid signature over M with respect to Vic. Okay, any questions? Great. So now that I have such a scheme, I can have schemes that implement, right, these 3 algorithms, and I want to be able to analyze, are these implementation secure, or do they fulfill specific requirements? For example, I want the existential forgeability requirements, which informally means that the adversary cannot forge messages. If the adversary does not have access to the signing key, it cannot forge messages. Okay? Now, this is the goal, this is the requirement, but I also have to explain what is the capabilities of the adversary, right? What is the adversary model? So let's start with a very weak model, a key-only attack. This is actually even maybe too weak, but in a second, I'm going to present a stronger adversary. So what basically the key-only attack means is that the adversary basically only knows the public key, right? Nothing else. And then he still needs to be able to produce, to forge signature over message. Now, the next step in the game-based approach is once you have a requirement and the model adversary, is to define a game. I'm going to define a game called game key-only attack existential forge dash existential forgeability, which will capture both the requirement and the adversarial model. And then what I'm going to do is I'm going to say that if the probability of any adversary that has the key-only attack capability to actually win the game, to be able to forge such a message, right, as we expect in order to break the game, then if this probability is negligible, it's very rare to it actually to happen, then we'll say that the specific signature scheme, right, the implementation that we actually analyze is existentially unforgeable under key-only attack. Okay? Great. So how would such a game look like? The game defines an execution process, a way for us to interact with the adversary. So we have a challenger, and the challenger starts by calling the key generation of the signature scheme, right? It gets the signing and the verification key. As the key-only attack states, it gives the adversary the verification key, nothing else. The adversary can do whatever it wants, but it needs at the end to provide us a message M and a signature sigma. And now we need to check whether the adversary won the game or not. So the criteria for existential forgeability is that the message M is a valid signature, right? According to sigma, the message M is validly signed using sigma according to the VK verification key, right? But I want you to focus on the fact that this game really couples together the model, the adversary model, with the requirement. Okay, questions? Now, let's say I'm fine with that. I can now actually prove whether a specific implementation is existentially unforgeable under key-only attack using this game, right? So I can now do like rinse and repeat for other requirements and other adversary models. So what I'm going to do now, I'm going to use the same requirement. I could have used other requirements, but I'm going to prove, I want to show you how you can prove that a specific implementation is existentially unforgeable under another adversary model, the chosen message attack, which is a stronger adversary that can actually choose messages and ask them to be signed, and it gets this signature. And at the end, again, we want to see if this added capability allowed the adversary to forge messages or not. But in order to do that in a game-based approach, we have to now define another game, a separate game, that will capture the CMA-EU game that will capture the requirement with the modified adversary model. Okay? Now, how would this game look like? Again, starts very similarly. We generate a signature key and a verification key. We give the adversary the verification key, but now we need to show how the chosen message capability works. So we allow the adversary to choose M messages, and for every message that we choose, we're going to sign the message, and we're going to give the signature to the adversary. And again, after this added capability, we expect the adversary to give us a message M and a sigma, and we're going to check, but notice that even the criteria had to be adapted to capture the different model, because now it's not enough to check that the message and the signature are valid. We need to verify that the adversary, because it's an adversary, right? He might want to cheat us, right? He might try to give us a message that we actually signed for it, right? So we want to make sure that he's not being coy with us, right? And he actually was able to forge a message, because this is existential forgeability. Great. And again, look at how these two are coupled, how the game bundles them together. Now, this basically results in this kind of a table where we potentially could analyze a lot of requirements with different adversary model, and we can, for each of them, prove whether a specific implementation satisfies or does not. Okay? This will result in all-time M adversary games, which is not that great, but they're our worst thing in life. Okay, you might say, we can live with that. Okay, and I will say in response, please wait. Okay, because now, if we'll take a slightly more complex protocol, or maybe even slightly more interesting, right, scheme, like a timestamping scheme, TS. A timestamping scheme is that in addition to a signature, right, you can also have a timestamp stating when this message was timestamped, right? So a timestamp scheme would look like this: 3 algorithms, key generation, a timestamp, and a var. Again, key generation gives you a signing key and a verification key. The timestamp will take data D with the signing key and will produce TS, the timestamp. Okay, now this is where I should emphasize that I intentionally did not write here sigma, because it doesn't have to be a signature, right? The timestamp could be whatever. We're going to use a signature scheme, right? But you could have implemented like this otherwise. So the timestamp will give you the timestamp algorithm will give you TS, the timestamp. And then you can verify whether data D with a specific timestamp is actually a valid timestamp. If it's not, the var algorithm will give you bottom, false. But if it is, you will not only get true, you will also get the time T of the timestamp. Okay? Great. Feel free to.
Where is T in the input? I didn't see T as an input.
You don't see the input because it basically will be part of the TS. Yes, exactly. Great. So we are now pros in game-based, right? So what we're now supposed to do is define the requirement that we want to true. And the adversary model, right? So we're only familiar with the key only attack. But what it means to be existentially unforgeable timestamping scheme? So let's adjust a bit the definition from the signature scheme, and let's say that we want the adversary to not be able to produce data D with a timestamp TS that is valid unless D was actually timestamped on time D. Okay, makes sense? Great. So what is the next step? Define again, right? However, there is a slight problem. We cannot just go ahead, because what happened here is that the way that I've defined this requirement, I actually assume another thing. I assume that the clocks are fully synchronized, right? But how can we guarantee that? What if we don't want to rely on that? We don't want to assume that, right? So, for example, what if a more realistic assumption would be that the local clock of the timestamper has drifted away from the real-time T, some kind of drift, could be short, could be long, right? So this means that now I need to address the notion of time when I analyze the protocol. And therefore, I have to specifically state what is the clock synchronization assumption. Is it fully synchronized like the previous definition here? We basically assume, right, if it was timestamp on time T, that there is no clock drift. The clocks are fully synchronized. But maybe I want to actually assume a bounded drift. So let me show you how would I change the definition of this requirement if I'm going to assume a bounded drift, okay? So the change is going to be that an adversary cannot produce data D and a timestamp TS that is valid unless D was timestamped during T minus delta or T plus delta, where delta is the allowed maximum drift, right? And this is maybe a more realistic assumption that I would like to analyze the protocol against. So now, in addition to the adversary model, I also have the clock synchronization model to be bounded drift. But this unfortunately means that first I need to kind of revise my previous statement that a game in game-based needs to capture both requirement and an adversary model, right? Because the more accurate thing will be that the game needs to capture the requirement and all the model assumptions. Could be adversary, but could be also a time-related, clock synchronization, network delays, etc. So this means that we're not going to have this kind of a nice table of game. We're gonna have something like this, right? When we have not only the adversary models and the requirements, we also need to address the time assumptions. So now we're gonna have R times M times C games. But obviously it never ends here. It's only the tip of the iceberg. And what about, for example, a protocol and improve or more interesting protocol of a distributed timestamping protocol where clients can submit data to be timestamped to a server. In this case, I will also have to account, right, for the network delay. So I will now have to say, is it a bounded delay? Is it a fixed delay or any other possible delay that I want to assume? And then I'm going to get R requirements at times M adversary models and clock synchronization and network models assumption, etc., etc. And this is going to be significant. Okay, great. So let's recap what we've done so far. We talked about the game-based approach, which gave us the ability to have provable security. We could have defined game. We could have proved, for example, using reduction, whether the specific implementation actually there is an adversary that can win with non-negligible probability or not. However, there was no modular specification. The game bundled together the requirement with the model assumptions, right? And we didn't have something called composition that I will discuss later, okay? and we really want composition, as I will show later. Now, I kind of skimmed over, I didn't really discuss another approach, a more trivial approach, the informal approach, where we can just make security arguments, right? So security arguments, they have advantages because we can have modular specification. I can basically argue whatever I want very modularly. I can even have composition. We didn't discuss composition, so I will not talk about it further now. But security arguments are arguments. They are not provable security. We cannot formally prove them, right? So although it looks like better, right? It has more ticks, but this is a key point that we really want to have. And this kind of drove us into working on CMoSS, and that's basically the predecessor of CMoSS, the Modular Security Specification Framework from Crypto 21. And in MoSS, we were actually able, I will show it in the table. So what MoSS gives us, MoSS is a game-based approach. But in addition to provable security, we can actually do modular specification. We can separate the requirements from the model. I will show you in a bit how we're doing. So this is MoSS, but what we've done in CMoSS, we extended MoSS to also to have composability, because in MoSS we didn't have composability, but in CMoSS we added composability, right? Now, there is another system that I'm not talking a lot about here, which is UC. UC is different, it's slightly different. It's not game-based, it's using something called simulation. And it basically gives us provable security and also composition. And this is the reason why UC is so popular. It's a very, very popular method of performing analysis, security analysis. However, it doesn't have modular specification. Again, it bundles together the requirements and the assumptions. Okay? So let me talk a bit more. Our goal in CMoSS is to have a trifecta, to check all the boxes, to have provable security, to have modular specifications, and to have composition, secure composition of protocols. So in the CMoSS, right, the core benefits or the goals of CMoSS is to have modular specification, but we can also analyze protocol under different model assumptions because the model assumptions are not bounded to the requirements. This will allow us to reuse specification. We can now define a model to one protocol, but maybe we can reuse the same model assumption to analyze other protocols. Because again, it's not bounded to specific requirements. We can compare protocols against the same assumptions. We can reuse them. And we can have secure composition, as I said. Again, I'm going to really skim over this slide because secure composition is a big thing. A lot of work, maybe the most famous work is universal composability, but there are so many other works in this area and with this direction of composability, like constructive cryptography and IUC, etc., etc. This is a very big thing, and we really, really would like to extend MoSS, like in CMoSS, to also have composability. And very shortly, I'm going to show you why. Any questions? Great. So, what I'm going to do now, I'm going to show you the basics of CMoSS and how it basically allows us to do what we're going to do. The first few slides will be the core that was already introduced in MoSS. And later, I'm going to show you how we're basically giving the C into MoSS, the CMoSS. And so our goal is to be able to prove that a protocol satisfies some requirements, some goal R, assuming some model M, right? But notice how they are separate. The requirement and the model are completely separate, okay? So in CMoSS, we have just one game. One game. But how can one game rule them all? How can we use one game to actually capture so many requirements and model assumptions? So the idea is that the game is adversary driven. The adversary has almost complete control on the execution of the game. We're basically going to ask the adversary, what do you want us to do there next? And we're going to do exactly what the adversary wants. What this actually allows us is to take an execution completely instructed by the adversary and to generate a transcript, a fully documented transcript of the execution. We're going to write the adversary wants us to do this operation on this entity at this exact moment with this exact value, complete control to depth. And then we can later take these transcripts, these executions, right? And we can make claims based on them, right? We can, for example, design a model assumption. We can define the model, and we can examine the actions that the adversary told us to do in execution. Do they follow a specific assumption of adversarial capability, right? We can then, for example, define the requirement and check whether the adversary was actually able in some execution to break a requirement or was not able to do it, right? And that's a bit vague, two sentences that I said, but I'm going to actually show you how I'm going to do that, right? So we have a single game, the execution process exec, and when we execute this, we're basically executing protocol P against an adversary A with input parameters params, and the output of this execution is the transcript T, the complete details of the execution. Okay? Now I'm going, because I don't want to do proof by intimidation, right? I'm going to show you the pseudocode, but before I show you the pseudocode, I'm going to show you an intuitive version of it, and then I'm going to show you all kinds of letters, Greek letters, and stuff like that. Okay? So I'm going to show you now this execution process that I just mentioned. And the first step in the execution process is to go to the adversary and ask it, and to initialize it, right? And then ask it which entities you want to have in this execution. Please choose. How do you want us to initialize them? The adversary is going to give us detailed instruction, and the next thing we're going to do, we tell the adversary, your wish is our command. We're going to do exactly. Okay? And then we're going to get into a loop, and we're going to repeat, go to the adversary and ask, now that all the entities that you chose are initialized, what operation do you want us to perform? Please choose an operation, choose an entity, choose the input to that operation on that entity, choose which local clock that entity will have, whatever. We try and really give the adversary almost complete control. The adversary is going to choose one operation, give us the detail, the instructions, and the adversary's wish is our command, right? We're going to do exactly that. Not only that, we're going to give the adversary, okay, the result of this execution. We're going to actually take the output of this execution and we're going to give it to the adversary. And we're now going to ask the adversary, are you done? Are you satisfied? Do you want to invoke anything else? And we're going to repeat this again and again and again, as long as the adversary wants to, whatever the adversary tells us to do. And we're going to keep doing that until the adversary said, enough, I'm done, I got everything that I wanted, right? So when the adversary tells us that, we compile the transcript of everything that occurred here, and this is what we're going to output. Any questions? Yes.
Do you know when, what if this never ends?
If this never ends, we don't care because the adversary, right? You cannot win if you never let this execution end. Okay? So basically what we do assume like a PPT adversary, right? So we do have some kind of an end to the scale, right? Any other questions? Yes.
So similar to that, how does the adversary decide when to stop?
So basically the adversary will decide to stop when he has what it needs to win, right? To break some requirement. Okay, but notice You didn't hear me anything here about requirement, about a model, some assumption. I'm not assuming anything. I'm allowing the adversary to do whatever it wants. This is why a single execution can actually capture so many models and requirements, and we can actually even extend this even further. I'm not going to discuss this in this presentation, but we actually have a built-in mechanism to actually even extend that further to allow to do stuff that we maybe couldn't have done here, but we can actually extend this execution without changing this. Yes.
So you only have a single game, but I guess to exhaust all those sort of boxes, right, in the 3D or 4D,
Right.
would you still have to go through each of those scenarios and say that, right? I mean, you actually satisfy that.
I'm actually what? Sorry.
So I guess inherently, right, do you still have to go through each of the boxes there, right, to say that, oh, this is satisfied, right, under that attack model, under this requirement, and under that requirement is actually satisfied.
Well, I can now choose, right, which ones I want to analyze, but I can take a single requirement, right, and prove it under different models. I don't need to create a different game for each requirement model combination. Okay.
Yeah, you don't have to do. I mean, you don't have to do that, right? But if at the end, right, you want to say that your protocol, right, satisfied all those nice properties, right, you still have to go through.
I still have to go through that, right? Because I cannot say, oh, if it won't be able to do the proofs for me.
Mm-hmm.
I will still have to provide the proofs.
Right. Okay.
Yeah.
Yeah. So how does the transcript capture like parallel processing? I guess the transcript will contain like a serialized event, right?
Right. We are performing each event and only then the next one and the next one, the next one. Now we can actually capture slightly more complex events here because you see we don't see it yet, but we do give the adversary really the ability to decide when an operation will be executed. So we do have the ability to do much more complex stuff. But if it's not exactly what you mean, you can also extend it. But I'm not going to show this. Okay. So let's look.
Yeah,
Right?
Hemi, can I ask a question?
Yes.
Yeah, first of all, can you please share the slides? Because I guess when your laptop get disconnected, we lost the
Yeah,
slides.
just a second. I will fix that.
Yes.
Let's try to fix this.
Yeah, great.
Okay?
Yeah. Thank you. So two questions actually, which is about the parallel composition. So by giving the adversary the freedom to pick any operation, this also implies that the adversary can instantiate like several sessions with several entities at the same time, right?
Yes.
Yeah, so if we're talking about signatures or I don't know, authentication, let me say, I can start like multiple authentication sessions at the same time with like the parties without being forced to end the first authentication session with the first party and then start the other, right?
Right. You can basically do whatever you want. Now, the thing is that in a second, I'm going to show you how can we basically filter out everything that the adversary told us to do, but we don't want to assume that it can actually do that.
Yeah, I got that part. I guess because within the steps you were talking about, you were saying that, okay, the adversary can choose the entity, the operation, the input, and then we will execute that operation and give the adversary the output. That operation is not supposed to be a full session. Hey, we ended the session for you. Here's the output. No, it could be like a part of a session and I can start another and they are still concurrently going on, right?
Yes, you can, well, it's not going to be in the next slide, but in the paper, the full version, we can actually, the execution process also allows you to have instances of the protocol on the same entity. And then each of these
nice.
has its own state. And then using this state, you can create sessions and do all of these flows.
Okay, cool. And maybe another question, which is about the like complexity of the whole thing, because yeah, the adversary is PPT, but now you are like, yeah, composing several like primitives or modules together, and each one has like the same PPT, but then when you compose all of these, you still want to be in the PPT realm. And I assume you guys also looked at that aspect.
Yes, but it's maybe I need to. But it's well, we can discuss it, but it will be after this talk.
Yeah, totally. I just wanted to know whether the answer is yes or no.
Yes.
That's it. Okay. Yeah, and I just want to say the following, that yeah, the talk so far is great. I really liked the motivation. It made it so clear why MoSS and CMoSS is needed. So yeah, thank you for that.
Oh, great. Thank you. Nice to hear. Yeah, I will just try to plug in my computer so it won't turn off every few seconds.
And while you are doing that, do you mind if you share the slides with us or make them available somewhere that we can get a copy of them?
Yes, but I guess I will have to do it only after the talk.
After, definitely, yes. But yeah, I'm saying it would be great if you can make them available to us.
Yeah, sure.
Thank you.
Okay, let's see. Oh. Okay, is it still shared or no? We're back?
Yes. Yeah.
Okay. The title is missing, but let's see if we can do something about it. Okay. Good. Great. So now we can actually show you the nitty-gritty. Yeah, sorry.
What is the criteria of adversary to win the game?
Oh, I will get to that. Great question, but I will get to that. Okay. So now I'm going to show you the nuts and bolts. Okay. So the first thing here you can see, again, I have a protocol P, parameters, and the adversary A, and I'm initializing the adversary. I'm giving him the parameter, right? The adversary in response gives me a state as adversary, SA. It gives me the entities N and the parameters that I'm going to be using to initialize the entities, right? Now, the next thing is to actually do the initialization of these entities. So for every entity in N, I'm going to initialize this entity. Notice that init is an operation of the protocol P. Okay, so we basically assume that every protocol will have such initialization, but if for some reason you don't need to do anything, just have an empty implementation, okay? Now, we are initializing the entity I, so for every invocation of this, we're going to get the state of entity I, okay? And we're going to give it the parameters instructed by the adversary. The next step will be to create this loop that we mentioned. And if the mouse pointer will actually work, that will be nice. So now I'm maintaining E is our loop variable, okay? And I'm going to repeat the following, increase E, and then I'm going to the adversary again. I'm giving the adversary the state from before, and I'm asking him, please tell me what to do. Your wish is my command. And the adversary is going to tell me, in the current event, in event E, please do the following operation on this entity with this input. And the local clock of that entity during this operation will be this. And the real time will be that. Okay? Now that I got all of these details, okay, I can now go ahead and actually do it. I can now take the operation from the protocol instructed by the adversary, do it on entity, right? E, and I'm going to take this state of that entity, which I initialized here. I'm going to perform that operation with the input provided by the adversary. I'm going to give the entity that specific lock, right? And I'm going to take the updated state after invoking the operation. I'm going to take out E, which is the basic output that the entity gave us after the execution. And I also have here a sec out, which allows me to actually output stuff that I'm not going to give to the adversary, as I will show you in a second, because the next step is to go back to the adversary, give it the state, and even whatever is in out E, because I want to be able to give the adversary full control. Later, I can decide what's going to be here or not. But notice that I'm not giving the adversary whatever outputted in this sec out. Okay? So I'm calling the adversary, and the adversary now needs to decide, do I want to continue or not? How the adversary decides that? The output that the adversary gives me contains the state, the updated state, out A, the output, and as long as the output is equals bottom, we're going to repeat this again and again and again. But whenever the adversary is done, it's going to give us some output here, and we're going to stop. And in addition, we're going to get F, the set of faulty entities, the entities that the adversary has compromised during the execution. Yes.
Yeah, I have a question. So, although you let the adversary start the initialization process, but the adversary cannot get access to every, right, like the secret key. The adversary definitely shouldn't get access.
Okay, so notice that I don't give to the adversary the states, right? The local state of the entity. Usually you would store a secret key in the local state, right? I do not give this to the adversary.
Yeah, I mean, like from line 2, right? How the local state get the secret key? It gets it through the initialization process, which is invoked by the adversary.
Well, but usually in initialization, you generate, for example, in init, you will generate the key, right? And you will store it in the state. And later on, if the entity needs access to that security key generated in init, it can access its own state that I'm giving it here, and this information will be there.
So you mean the initialization process is started by the entity itself instead of the adversary?
The adversary, right, decides which input we're going to give to the initialization, but you actually perform the initialization over the entity itself. It's not, this is an important note, the adversary is not initializing the entities. We, the execution process, is actually interacting with the entities, okay? The adversary just tells us what to do. And so finally, if the adversary tells us, okay, I'm done, this is the output, so what I'm going to do now is I'm going to collect into T the entire execution. You see, I'm taking everything. The adversary outputs, the events, the entities, the faulty entities, all the operation that were done during all the execution, the inputs, everything, and I'm just outputting it out. Okay? Now I'm starting to get time constraints, so I'll try to speed up somehow. So the next step is, okay, so I have this transcript, right? How can I actually measure whether the adversary behaved according to some guidelines, to some assumptions or not, right? So I want to be able to say whether an adversary A satisfies the model M or not, okay? So how do I do that? I will say that adversary A satisfies model M if for every protocol P, M holds for almost every execution of A and P. Now, almost is not exactly cryptographically defined, so we can define it more precisely, right? Like the following. So I will say that A satisfies model M if for every protocol P and params in this, the probability of a transcript, right, from an execution of A and P with params, the model will say bottom on that transcript, right, if this probability is negligible. Okay? So But how do I define such a model? Right? I show you the execution process. How can I try to check whether an adversary followed the assumptions or not? Okay, so let's see an example. I'm now going to show you the model of the key-only attack that we discussed before. Okay, so notice the model gets a transcript T, and now it can check whether there is an event during the transcript, during the execution, right, where the operation on that event contained the sign operation. This means that the adversary asked to sign something, but we do not want to allow the adversary to sign anything in the key-only attack, right? Now, this is just a simplified implementation. You can define, obviously, other models, and you can be more relaxed or more strict the way that you define this model. Let me show you another example of a model that we discussed, the drift. You remember the bounded drift, right? So again, we take T and we say for every event in T, we do not allow, we bound the difference between the local clock in event E and the real-time clock to be at most delta clock. If there will be an event which this does not enforce during the execution, the output will be that it does not satisfy them. Okay, we do not want to consider such execution because it does not satisfy this model. Okay, great. So, yeah. Stop. Computer froze, I think. Okay, we're back from a while. So I remember I want to be able to analyze whether a protocol satisfies a requirement assuming some model. So how do I define this? So we say that the protocol P satisfies a requirement R under the assumption of a model M, okay? If for every adversary that satisfies M, the assumption, right? And for every pass, the probability of a transcript of an execution to be not held by the requirement R, which I'm going to define in a second, is negligible. Okay? So similarly, I can now define requirements and prove whether execution of a protocol will satisfy these requirements or not. Okay? Yes?
Is this the probability is the element of negligible parameters? I mean, or less than negligible probability?
It means so it basically means that it's very, very rare. It should not happen unless for very, very random rare cases. It's like, so it basically means that the adversary cannot actually break the requirement unless for some weird case that just happened. It didn't really that the adversary was able to break it. Okay.
So another thing, like, so when the probability is like greater than 0, like when
It can be greater than 0, but it should be very, very small. Infinitesimally small. Okay? Because again, the adversary can do something and miraculously it will work. It can guess, right? But the probability of the adversary to actually guess the right value is really, really rare. Okay? Great. So how would we, for example, this is a bit intimidating. Don't be intimidated. I'm here with you. I'm going to take you step by step, okay? So how will we define requirement for existential fungibility for signature scheme, which we mentioned earlier, right? So notice, we're getting a transcript T, and the adversary, we expect the adversary to output in out a message M and a signature signal, okay? And now we demand the following. First of all, right, we want to be able to well, I'm going to skip a bit because what I'm going to do now, I'm going to take this M and sigma and to do a verify on M and sigma, right? To see if the adversary was able to forge or not. But in order to do so, I need the verification key, that right? So I'm going to demand that there will be an event where on that event there was a key gen operation that generated the key. And since there is an event, because if not, I'm returning true. The adversary cannot win the game if I cannot verify a signature, right? So this is a demand. If the adversary, if there was no key generation operation, the adversary cannot win, and therefore I'm returning true because the requirement holds. The adversary didn't win. But if there is such event E, I'm going to extract from the output of that event the verification key, right? That the entity outputted. And then I'm going to check whether the adversary was able to forge or not. If this is, again, false, the adversary lost. It wasn't able to forge a message, right? But if everything checks out, I'm returning false because the requirement didn't hold. Because the adversary was able to give me a message M and a sigma, which is valid, which is true. Okay? Okay. Great. So you are now semi-officially MoSS certified. Whatever what we did by now is basically the core of the MoSS work, right? These basics, 3 parts: the execution process, the models and the requirements, and the definitions of what is an adversary that satisfies a model, what is a protocol that satisfies a requirement under a specific assumption. But what we're interested in CMoSS is to also add secure composition. And let me please motivate you why we want it and what is the power. Okay. So what I'm going to have now, I'm going to take the timestamp scheme from before, right? And I want to be able to take a specific implementation of that scheme. Let's take, PSTS timestamping protocol, a specific implementation of these 3 algorithms. And the reason that I'm using PSTS is because this implementation is going to rely on an underlying signature scheme, okay? Notice this is sort of a black box, right? Where the implementation of this protocol is going to rely on a sub-protocol that will implement these 3 signature scheme algorithms, right? Okay? So, and this is actually how we design protocols, right? We rely on underlying protocols. So how this kind of work in practice? So whenever someone will ask the timestamp, right? It will ask, okay, please perform the timestamp operation of the TS scheme, right? I will do a call to the sign operation of the black box of the signature scheme. I will get back the signature, right? Sigma from the black box. And now I can do whatever I want in order to take this sigma, so I'll be able to return here the timestamp, right? Okay. Now, how we in CMoSS, how will we actually design the pseudocode to reflect such an implementation, right? So in the PSTS timestamp protocol, we have the key gen operation of the timestamp, and notice how inside it in the implementation, it calls the key generation of the signature scheme, right? And in the implementation of the timestamp of TS, we are calling the sign operation of the signature scheme. And then we can take the signature and output this tuple of signature with the local clock, because we are signing not only the data, but also the local clock, right? And the final algorithm is the var of the timestamp, and we're just going to call the var of the signature scheme, right, with the data and whatever we got here in the timestamp. Okay? And again, I want to emphasize, notice how this implementation doesn't care about the implementation of the signature scheme, right? I just want to rely in the timestamp protocol that these exist, right? Now, the thing is that I cannot take this and analyze whether it satisfies some requirement or not. The reason is this is missing. This is not a complete protocol because it has this black box. If I want to analyze the implementation of this protocol, I need to explain what is the implementation of the black box. Okay? So, for example, what we can do now, we can choose an RSA signature scheme, complete implementation, right? And then we can analyze whether the PRSA the RSA-based timestamping protocol is secure or not. What I mean by secure, for example, is it existentially unforgeable or not? However, this is the key. If I will do now a small change, and instead of RSA, I'm going to use elliptical curves, I will now have to redo the analysis. I can no longer say, oh, I already proved it for RSA based. I will now have to reanalyze because I've changed the implementation. Maybe that affected to the satisfaction of the requirement or not. Okay? But what we really want to be able to do is to design this protocol and not only to assume a signature scheme, to assume a secure signature scheme. And once we assume this, we require this from the signature scheme, we don't care the implementation. We're going to prove that give me any secure signature scheme, prove separately that the scheme is secure. This property or whatever property that I'm going to prove holds. Okay, and that's the key, that I want to be able to prove that this protocol satisfies specific requirement, assuming any secure signature scheme. I will not need to redo the analysis. Okay, great. So what I'm going to do now, I'm going to change a bit the illustration that I did before. What we want to do is to have a protocol P that satisfies a requirement R, okay, assuming model M, but also assuming a black box. A requirement, for example, if I will take the PSTS protocol, I want to be able to prove that it is existentially unforgeable, assuming some model assumptions, and also assuming an underlying secure signature scheme, or specifically a scheme that it satisfies the existential unforgeability for signature scheme. I don't care if you're going to give me RSA that you've proven it to be existentially unforgeable under some model M1, or if you're going to give me elliptical curves or whatever, because I'm going to prove that as long as this is satisfied, I don't care about it. Okay? Great. So, first question. I'm talking about composability, about composing two protocols together. I want to emphasize this. Maybe that's an important note. I'm going to compose this protocol with this protocol or with this protocol. So I'm composing two implementations together to a single implementation. Right? So it begs the question, are any two protocols can be composed together? Okay, so you can read this. But I will just give you the simpler the bottom line is that basically almost yes. What I mean by almost yes. First of all, how do we define composition? We define composition of protocols using union, simple union operation. So if I have a protocol P with two operations, P OPR1 and P OPR2, and I have another protocol P prime with P prime OPR1, notice the same OPR1 but different protocol name, right? If I'm composing them together, it's their union. So I get this set. Now, basically, I can do that to any two protocols as long as I can make their operation distinct. So I could not have do this union if these two protocols were called P and they both had an OPR1, right? But as long as their full name is distinct, I can refer to each of these operations directly distinctively. Okay? So we answered the fair question, are any two protocols are composable? And notice that I'm using this notation that I'm composing these two protocols because we want to convey that you can actually now compose another to this and another like a jigsaw puzzle. You can design your protocol like a jigsaw puzzle. Okay? So the next question is, if a protocol P satisfies requirement R, assuming a model M, does it mean that every protocol P prime that is composable with P, does it immediately mean that their composition also satisfies R under M? Again, if P satisfies R, assuming M, does it mean that every composition with P also satisfies the same R, I'm assuming the same M? Okay, so unfortunately, the answer is no. And why is that? I can actually show you a simple case that this doesn't hold. Okay, so let's, for example, have this requirement. Some strange guy decided to define this requirement, which is R42. Okay, and what R42 requires is that if there is an event during a transfer with an operation foo, and the output of this operation contains 42, the requirement does not hold. In every other case, it does. Okay? So let's take a protocol P that satisfies this requirement, and P satisfies this requirement because we're going to say that P simply does not have the operation, right? So this can never happen. But if we're going to compose P with any P prime that does have such operation that will output this, even though P satisfies R42, the composition will not satisfy. Okay? Yeah.
Yeah, I have a question. So, but it does have like transitivity property, right? So if P satisfies requirement given model and P prime also satisfies the requirement given model, then the union of the two will also satisfy it.
Oh, wait. So I'm about to get to all kind of properties, right? Nothing is trivial. We have to prove everything, right? That's the problem. We can't make an argument, and if we think that it's trivial or it does happen, we have to prove it. Okay? Great. So we've answered the previous question that no, not the fact that this happened does not immediately implies that this will happen, right? But there is an observation, important observation. Does it hold for practical cases? Because I guess we can agree this crazy requirement is not exactly practical, right? But would it hold for practical cases? And the interesting answer is, would it hold for this? And the instant drum rolls. They actually, we're able to find. Now, I want to clarify, we found a way that this works. It doesn't mean that this is the only way or the best way. There could be other ways that this will actually hold, But this is a way that we find, and maybe in the future we will be able to find a better way. Okay? So what we find, and we show it in the paper, that if we're going to take P-composable requirement. A P-composable requirement is a requirement that has two properties. You see, it is we say that requirement R is P-composable if it is specific to the operation of the protocols. And intuitively, you can understand why. In the previous example, right, the requirement was not specific to that protocol, and then when we compose it, it broke, right? But it will actually require it to be specific to the protocol, right? And also we will require that it is also something called input type independent, and unfortunately we don't have time to explain what it is, but you can read it in the paper, okay? So if we will have these two properties for requirements, then we'll call it a P-composable. And we'll have a P-composable model, which are models which are input type independent, like I already explained it here, I don't need to explain it again. And also something called ops eavesdropping, which again, I don't have the time, but you can see it in the paper. If these two happen, we can actually make the following theorem. We can actually show that for every protocol P prime such that it is composable with P, if P satisfies R under M, it means that the composition of P with P prime under M also satisfies R. Okay? If the model is P-composable and the requirement is also P-composable.
It's interesting, right? Because it doesn't say anything about the P prime, right? And then how the composition is just a union.
Exactly, but because the requirement is P specific, right? We don't care.
Oh, okay.
And that's the power of it, right? Now, again, maybe we can have other like definitions of the P-composable, right? And then we can even have stronger, right, to include more cases. Okay, and I'm getting to the end. So this is another kind of illustration, right, that I want to show. Basically, stuff that we already saw. For example, RSA satisfies existential affordability, assuming some model. And I want to say that PSTS satisfies this requirement under this model, assuming this requirement and implementation. So now, if I'm going to give you this, does this imply this? Okay? So, first of all, we are going to make the following definition. Protocol P satisfies requirement R, assuming model M and a black box requirement R prime. This is basically this, right? So what does it mean if this happens, right? It means that for every model M prime and a protocol P prime, such that P prime and P are composable, if the composition of P with P prime satisfies R prime under this model, their composition also satisfies R. Okay, and again, this is just the formal way of basically say, right? Oh, too much. If this happens, right, then this happens. Okay? So now that I have this definition, right, the definition of this, we can now actually have a lemma and prove that if I have this, okay, and a protocol P prime that satisfies R prime under M prime, just P prime, not their union, okay? If I have this and I have this, I immediately get this, that their composition under this model says, this is the secure composition, okay? Yeah. Now, the only thing left to do is actually discuss, wait, you define this, you show that the composition of, not here, okay? But how do you do this? Because how do you actually prove that the protocol satisfies this, assuming requirement? This is not trivial. I showed you how you can do this under a model, but how do you do this with a requirement? Okay, and this is definitely something that we had to explore, because what you basically, it really brings you to the world of inter-process communication, right? You have one process talking to operation of another sub-protocol, right? They need to somehow interact. You're going to introduce, for example, asynchronicity. You need to discuss all kind of, think about or get inspired by compiler and operating system, the way that they are doing this kind of stuff. So the immediate question is how to prove satisfaction of a protocol assuming a black box, right? And what we found that we can actually do that if we will define and require this model. It's called the IRI model. IRI stands for invoke return interactions, okay? And we basically only demand relatively simple demands. So first, again, this is a model. We already know what models are, right? What do we demand from the model? We demand timeliness. If we are going to execute an operation of a sub-protocol, we expect it to be bounded to finish sometime, right? Otherwise, we won't be able to finish the execution, right? So we demand that it will be bounded. We also demand that for every entity, every event that was executed on a non-faulty entity, okay, the inter-entity co-integrity, that it was actually completed as it should, that you invoke the sub-protocol, you gave it the right input, you got the right output, you invoke the callback. Remember, we have an adversary lurking here, and the adversary has full control. How can we actually assure that the adversary behave, and maybe the adversary chose to change inputs, outputs to don't complete the intercommunication, inter-process communication, right? So this actually, and now you see it just as a call, you can see, so algorithm, we actually describe each of these sub-algorithms using the pseudocode. You can actually verify, does it capture what you're trying to say? Okay. And also, look, I can explain to you something relatively complex. And now you can take each of these sub-algorithms and check it very easily, because you don't see like a huge algorithm. And the last thing that we require here is inter-entity communication confidentiality. And why is that? Because if we're talking about an entity which is not faulty, we don't want the adversary to be able, right, to read the data that transfer between these calls, right? Okay, so I'm really out of time. So to conclude, we discussed CMoSS today, which is a huge step in the right direction to have provable security for applied cryptographic protocol for complex protocol and the realistic protocol. We actually already used MoSS, the most part of CMoSS, to prove and to analyze protocols which are complex. For example, PKIX, which Sarah discussed last week, right? And there is another group with Professor Herzberg and with Professor Lada, right, that work on using MoSS for blockchain, obviously applied, right, obviously complex, distributed, right? So a lot more interesting things to do in the future. And definitely when we now have the composability in MoSS, this is a huge thing that will be able to actually define and analyze the protocols in a modular way, right, to have and to rely on the secure composability. That's it. Thank you very much. If you have any questions, I'll be happy to answer. Questions? Yeah.
Okay, I was just curious if we have multiple components that you also treat as black box, does it also do this, like iteratively? Could you-
Yes. It works. We actually prove it in the paper. You can actually now take a compose protocol and compose that and compose that, and exactly you get this huge benefit. Exactly.
Yeah, I think I just had a question with the composability definition, right? I think somewhere in the slide you said if P and P prime is composable, then if P satisfies a requirement, and then the union of the two will also satisfy the same requirement, right? I just really want to know like the precise definition of being composable, right? So P and P prime, they can have like no operation intersections or something like that.
So when the way that we define composition, right? We demand that you won't be able, the union must not have any mutual operation, right? The full operation name must be distinct, unique, in order for the union to contain all the operations from this protocol and all the operations from the other protocol, in order for us, when we have the composed protocol, to directly invoke each of the operations of the subprotocol.
Yeah, but is it just the name, or there are also some limits of the operation itself, right?
Okay, so they're basically just the name. And the reason is that once we say the two protocols are composable, it does not immediately mean that you get all the things that we said. We simply created a union, right? The thing is that once we took this composed protocol, their union, now we could make these arguments that we make and show that for some cases, not every case, right? Not every composition you immediately get a secure composition, right? For some interesting cases, you can definitely have secure composition.
Oh, okay. So you're just taking a union there, right? In order to prove that this is actually a secure composition, you do need like.
But that's not immediately followed for every union, right?
But the property is that if the protocol satisfies some property without the union, it would still satisfy its requirement with the union, right? So we don't show that the basic property does hold all this, right? That you don't lose some requirements which you already satisfy. The question is, do you gain by composition? That is what you need to do this extra work, right? But just for not losing a property, that is enough for them to not interfere, right? Like it's, again, so the requirements which are kind of normal requirements, right? The requirement is not looking at that version that the protocol is not doing, for example, right? Because then you could have this 42 example in which this real example in which yes, suddenly you compose a protocol in a requirement which was kept, it's not kept because this requirement is kind of weak. Real, it's looking at the information the protocol is not even doing. But then suddenly it's doing and something is breaks.
Okay. Thank you very much.
Thank you.
Yeah, thank you so much.
Thank you.